Okay, here we go. That's better. Okay, so we care a lot about type 1 error. We announce it to the world, right? We set alpha. We set alpha at 0.05. We care about it so much, in fact, that there is a law in Canada, for example, when you report a political poll, you have to report the alpha. That's why they always say this poll is accurate, plus or minus 2.5 percentage points 19 times out of 20, if you hear it on the news. Because they have to. It's literally the law. And that's because it's important to know what the chance of a type 1 error actually is. Okay. Our software gives us exact p-values. When you play with SPSS, it'll tell you. We saw this just the other day when I was playing with some, what was it, a t-test we messed with, and it told me at 0.00001, right, for that those data I cooked. So our software gives us the exact probabilities, p-values of getting a type 1 error. Why is type 1 error more important than type 2 error? This is a rhetorical question, obviously, because it isn't more important, but we seem to treat it that way.
Because it probably increases the risk of type 1 error?
Well, I mean, if you have, what increases the risk? I'm sorry.
Like if we reduce the type 2 error, but however...
Oh, if you reduce type 2 error, you'll also going to, if you reduce the, sorry, in some ways, if you reduce type 1 error, you increase type 2 error. Like you'll see how there's a trade-off we're going to have here. There's a trade-off here, right? So if we can make a type 1 error completely likely, basically, by making it, well, let's be ridiculous. What if we set the alpha at 1? If there's a type 1 error, we're going to make it. We just say, no matter what happens, we're going to say it's significant. You'll find it then. Of course you will, because you set it up to always be that way. But you're going to make tons of type 1 errors in that case.
Yes.
So, well, I've got a couple thoughts. I can't read a thing on there. A couple thoughts here. Well, historically, Fisher, who I've talked about before.
Dave?
Yeah?
I need a black thing that goes on the screen. There's nothing next to it.
I don't know what a black thing that goes on a screen is.
You write on the blackboard here.
You mean a marker?
Yeah.
Yeah, well, I have markers, but I need them. Oh, those are, like, take it.
No, here. This thing.
I don't care.
Okay, you got the red one.
It's yours.
Yeah.
My free gift to you. Act now.
All right, I'll bring
Operators are standing by.
Okay, Dave.
Okay, so, Okay, so Fisher actually thought that our hypothesis was real. We know that it's actually a straw man, right? Like, we don't really believe the no. You ever set, most of you haven't set up experiments, but do you think that people, you will next year, right? But do you guys think that people set up experiments going, I think it's possible that nothing is here? No, we tend to set up things going, we think there's something here. So it's a straw man, but Fisher didn't believe that. He thought it was a real hypothesis. All our methods are set up that way. That's obviously circular. I'm asking why our methods set up that way. Because all our methods are set up that way. That's not a very good point, Dave. Now, it's easy, I think, for us to imagine a situation where nothing happened and to set it up. Say, look, here's the math. The two means will be equal. That's an easy thing to imagine, and it's an easy thing mathematically. To set up, I just say the means are equal. That's easy. So I can do that. The other thing is for HA to be true, for us to say HA is true. Okay. We have to know how big an effect it is. Like if we say there's no effect, we just say, no, nothing happened. If we say something happened, now you have to say, what happened? And that's a problem, because we don't know, because we haven't done the experiment yet. See what I'm saying? We have to think backwards, and it's a weird way to think. So we don't know how big the effect is. We don't know how big the difference is. So we have to kind of make some guesses. There's a lot of sort of guesswork that's going to be involved here. Okay? They give out free markers. They're in the supply room. Anyway, right. So the best of all possible worlds, we would minimize alpha and beta. That's the probability of a type 1 and a type 2 error. And that would give us the most power we could get, because remember, power is just 1 minus beta. Power is correctly rejecting a false null. So we want that. If it's there, we'll find it. And we don't want to make type 1 errors. Okay? That's our hope. So power is the probability of rejecting HO given, that's just a notation, okay? Given HA is true. The line like that just means given. So given that HA is true, what's the probability we reject HO? And that's what power is. We want that to be a big number, as big a number as possible, and we want alpha to be as small a number as possible. By making 1 minus beta as big a number as possible, we're making beta as small a number as possible, so we're obviously doing that as well. Okay, so I think conceptually this makes sense, right? Like, that's what we're trying to do. And I know you've had a lecture before in 2126 on power. And I'm sure it was really confusing, because this stuff is confusing to think backwards. So ask questions is what I'm saying. Okay? Right. So that's what we have. Power is the probability of rejecting a false null hypothesis. Let's look at a picture. Let's see if this is going to be any good today, because I probably should put an IT ticket in. These are awful, eh? The brightness? They weren't like this last time, right?
No.
Okay, because these don't work that well. Okay. So let us imagine a situation where this is the distribution for whatever the variable we have for HO, that's the null, and this is what we find, H1 or HA, whatever you want to call it. Okay. Note that I had to imagine where I'm putting this, so that's already, I think, a big step. We don't typically know this information. Okay. I think, let's see here. What I'm going to do is I'm going to move this here. Yeah. I'm going to put it over there, because I got a couple of things I want to say. How would we increase the power? Now, power is 1 minus beta. Take a look at this. There's beta. 1 minus beta is here, power. So, to figure out the power, we're assuming that this is H1, that that's the distribution. That's a pretty big assumption, because we don't know how big the difference is. We're going to have to make a good guess. Now, how are we going to make this region here bigger? That's what we want to do. And I want you to imagine you can do anything. You can do whatever you want. How could we make that bigger? How do we make this unshaded area here, this is power, how do we make that bigger? Any thoughts?
Decrease alpha and beta.
Pardon me?
Decrease the alpha and beta.
Decrease the alpha. Let's see. If we make alpha smaller, well actually if we make alpha smaller, that's going to move this line over. It's actually going to give us less power. Increasing alpha would. What if we put alpha all the way over here? We'd never do that. That's stupid. But what if we did? We'd have lots of power. We'd make all kinds of errors. We'd have lots of power. So increasing alpha would be one thing we could do. What else could we do? Take a look at that. Imagine you can do things you can't do.
Decrease the beta?
What's that?
Decrease the beta?
Decreasing beta is just increasing power. So you're just saying, how do you have... What you're saying is the same thing.
Same thing.
Yeah, so, yeah, because decreasing beta increases power. So it's the same thing. So, but how do we then decrease beta? Take a look. See, you're right, but you're really just answering the question with the question. Take a look. What else could you do? What if we just made the two, what if we took the distribution on the right and put it over there by the door? So they don't overlap anymore. That'd work. We can't do that theoretically, practically, but let's pretend we can. So we can move it over. That's not practical either, because I can't move variable values. It's not something I could do. If I could do that, you'd all be lining up on Sunday to worship me. Right? Or well, you had a thought.
Increase the sample size?
Okay, but what would that do? You're right. You're right. Of course, from the quiz we just had, right? Should have given you some clue. But increasing the sample size will do something to the bottom of the fraction right? What we're actually doing is we're making the variance smaller. What we're going to do here, what if we could just suck these in? Less overlap, which is actually what would happen if we increase the number of subjects. And I'll explain why in a sec, but you're right, that's the practical thing we can do. So we can make alpha bigger, but that's stupid. Like, we wouldn't do that. You probably wouldn't do that. It's very rare when you want to mess with alpha. We can increase mu1 minus mu0, but how? We can't really. Again, practically we can't. The numbers don't know where they come from, so if we could just tell the numbers all go over here, that would work, but you can't really do that, right? The thing we can do is decrease sigma. So that's decrease the overlap. Because remember, sigma is how spread out these are. Sigma is how spread out they are, and we're going to do that by getting more subjects. Okay, that's how we're going to do this. All right. So we're going to decrease sigma. We're going to tighten these distributions up. That's what we're going to do. And that is the thing we can do, and we don't have to be godlike to do it. You can just do that by getting more subjects. Okay? All right, questions so far? Okay? I'm going to do a lot of this stopping to check, ask if you have questions, because like I said, this is probably the most conceptually difficult one in the whole year. Okay. So our best bet is to play with the variance, the overlap, right? So making the variance smaller will tighten the distributions up, and that will mean less overlap. If there's less overlap, it's going to be easier to find the difference. Now, the thing is, we aren't dealing just with sigma, or sigma squared, we're dealing with sigma squared sub x bar, which is the sampling distribution of the means variance. Well, remember, the sampling distribution of the mean, according to the central limit theorem, which is really important to statistics, right? Right? The sampling distribution of the mean, its variance is sigma squared over n. Oh, look, there's something we can play with. What Arwen wanted us to do, increase the number of subjects. She's right. She's right. This doesn't change, the sigma squared doesn't change. You know what does change? If we make alpha, make n bigger, it makes that whole quantity smaller. We actually can do this. We don't have to be gods to do this. We do to move variables around. We can't do that. When we can't practically change alpha to like 0.1 or something, even though maybe we should sometimes, as I talked about earlier in the course. All right. So what we want to look at is how big, so we're going to have to probably do some calculations. And the way we're going to do this is we're going to have to make some assumptions. And one of them is going to be, we're going to have to say, how big is the difference between mu1 and mu0? If the effect is there, how big is it? And remember, a difference between two means says one thing, but we have to also worry about how much overlap there is. So we have to standardize it by dividing by the number, by dividing by the standard deviation. So we're going to have a quantity called d. D just means difference. And it's mu1 minus mu0 over sigma. It's just how far they are apart in standard deviation units. We're just putting it into standard deviation units like we do all the time. You know, we do that with z's for make z scores all the time. There's nothing fancy or new we've done so far. We just gave this thing a name. We called it d for difference. Okay? All right. Well, how are we going to know how big that's supposed to be? Look, that's the thing. It's all great to write down, yeah, mu1 minus mu0 over d. We're going to do it, make that up. And how are we going to know? I don't freaking know. The best thing we can do probably is look at prior research. So let's say you pull out Well, you pull out all kinds of, you'll do this when you do your thesis, right? You will get all kinds of old data and you'll be putting it all together. You'll be doing a literature review. Take a look and see how big the differences are, right? Most of you have taken 3286, right? The pre-thesis course, right? And you got all this stuff together. You'll probably find that there's similar methods used in the problems you're interested in. Take a look and see how big the differences are. That's one way to do it, right? So, but how big is big enough? Like, how big is a big enough difference that you think it matters? Because almost any variable, we have two groups. If we have enough observations, we'll find a difference. Does the difference matter? Probably not. So, I bet, I'm just trying to think of something that has no, I'm just going to guess the people on the left side of the room, so that's you three, me, that's it. Us, compared to you guys, I bet we have bigger big toes on average. Because of me, I'm 6'1", so I'm probably the biggest big toe in the room. That's probably why it would make us big. And it's probably real. Like, it's real, you can measure it. Does it matter? Well, no. Unless it's some kind of toe competition. You're all looking at my toes now, happily. My wife will be happy I am not wearing socks with holes in them. When I leave the house, she says, "Are you going to teaching socks today because of your boots?" And I say, "Yeah, probably." It's like I'm talking. It's like my mom's talking to me. "Do you have holes in your socks?" I would say, "Well, what do you care?" I'm embarrassed. That's why I care. Fair. Who cares what the size of your toe? But there's probably is a difference. You know what? There's probably also, we could, in this room, I guarantee you, the person with the biggest big toe, knows the most psychology. Does that matter? No, but it's true. So there can be real effects that don't matter. There is a difference between almost any two groups of people in almost anything you measure. And sometimes if you get enough of those folks, you can literally find a statistically significant difference. And who cares? Right? It's like, it's like you talk about sex differences in spatial ability or verbal ability. Those are real. There's a difference between men and women in spatial ability. Men on average are better than women. There's a difference between women and men on verbal ability. On average, women are better than men. It doesn't affect anybody's daily life. It's a neat, interesting result that doesn't matter. That's what I'm saying, right? So what if you find a difference between your two groups, but there's so much overlap and there's so little difference that it's not practically significant? There's statistical significance, which we draw a line and say 0.05. There's practical significance. Does any of this really matter? No! Who cares how big your toe is, right? Well, it's really big. If you have a really big toe, you know so much psychology. Things that come out of my mouth. Years ago, about 20 years ago, a couple students put together, they took quotes of mine. This is really weird. I'm not asking you to do anything like this, obviously. And they gave me a book at the end of their time here that just had weird quotes that I said, with little drawings and stuff.
They still post quotes in the Discord.
Good. I like to hear that. Is it things about the bigger your toe is, the more psychology you know. But it's true. Paul and I are probably the biggest big toes of anybody in our department. And Paul and I are smarter than Dwayne. Not smarter than Karen, so maybe that doesn't work. Maybe it's only among men. All right.
Imagine doing this research.
No, it's not doing the research. It's writing up the grant. And then the granting agency looks at this. Well, there's a reference here to a fucking YouTube video some guy. I don't know, some statistics thing? Yeah, sure, give him the money. Right. Okay, so how big is big enough? That's the question, and we can answer that by looking at, this is a guy named Cohen. Cohen's method of determining how big is big enough. So he said the following: we can have small, medium, or large effects. This is completely arbitrary. This is just this guy came up with 3 values and said, small, medium, and large. 0.2 is the difference. Is small, medium is 0.5, and large is 0.8. Look at how much overlap there is between the distributions of those 3 levels. At the small level, they are 85% overlap. And even medium, 67. And hell, the large effect, oh, it's so big. They more than half are the same. Right? I would typically, when you do these calculations, you go with medium, just because it's easy to do. It's just not easy. It's just that you figure, well, I'll take the one in the middle. I would always go with large, personally. But that, again, that's me. I'm pretty conservative scientifically, so. So what you're doing is you say, I want that difference to be, let's see, 0.8 or 0.5 or 0.2 or whatever. It's shocking, though, that what people call a large difference, still the two distributions overlap by more than 50%. Okay, that's not a large difference. That's a difference. I would have started there and called that one small. A lot of things we have in really life sciences in general, psychology, biology, basically in any life science, it's such messy stuff. We're dealing with complicated systems that the outputs are more fuzzy than they are in physics or chemistry, that's all. The outputs are fuzzy. So if the outputs are fuzzy and the inputs are fuzzy and the gear's fuzzy, you're going to get lots of overlap. That's sort of the way I figure. All right, where am I? Here we go. Well, now what? So fine, I told you to pick 0.8 or pick 0.5, whatever the hell you want to do. Just be transparent about it. Okay, so we combine this information with the effect of sample size. We're going to try to determine how many subjects, I'm just going to keep saying subjects, it's a stats class, how many subjects we need to have a certain level of power, that's the D, okay, difference, at a certain alpha level. That's what this is doing, these power calculations. Okay. We come up with something called the delta statistic. That is a small Greek letter delta. I don't want you to get too worried about the delta statistic, what we're going to do is I'm going to work through how to do this calculation, but typically what you do when you do this is, first of all, you look it up, because nobody remembers these things by heart typically. You actually, there are tables you can go to and say, I want this much power, there are this many groups, how many subjects. This is what's behind those. So delta, it says here, equals D, or times, okay, times how times how N affects the difference. That's what F and N means in that case. So how N affects the difference between the two distributions. All right. And I know that sounds a little bit esoteric. You'll see in a sec. It's actually not that complicated. Right? So F and N is how N affects a given test. So for T, F and N, we just would use square root of N. Because look at the T formula. What you have to do in this case, just look at your formula and say, okay, well, T equals, let's just use this one. No, it's an S, David. Oh, there's the N. It's a square root of N on the bottom of the formula. We'll use square root of N. That's how you do this. Like, it's literally that simple. You look through your formula, try to find where N is and see what have we done to it. Are we squaring it? Are we taking the square root of it? Or are we just leaving N by itself? And that's what that means in that case. So in this case, then, it's square root of N. And you'll see in a sec how we use this information. This actually isn't as bad as it seems. So what you're doing, so if you know D, when I say no, you don't know it, you're saying we want this size or bigger. So if we know D, and we can then figure out the sample size for a given power. That's what you're going to want to do. So you can figure the sample size out for a given power, okay? So let's say we know D is 0.5, and that's a pretty common one. It's the, quote, medium size. And again, you don't know what you're saying. That's as big as I will accept as that matters. Okay? You'd usually pick 0.5 because it's in the middle. I think 0.8 is probably better. But people usually pick 0.5 to do these calculations. And we'll say we want a power of 0.8. Now you just look it up. literally all you do now is look up in the appendix of the textbook. There's an appendix called power. And hopefully it shows up, because I show you how to do it on here, but it's so dim. We'll find out in a moment. Okay. So all you're going to be doing here is just using a different table. You're just using T tables, Z tables. This is just the power table. Okay. Now, this is the problem. So, if we say that D is going to be equal to 0.5, that's the difference we're interested in. We're saying 1 minus beta is going to be 0.8. We want a power of 0.8. We want a difference of 0.5. Okay? And again, we picked these. We pulled these out of our collective asses here. Okay? This is something we just made up. We don't know this. We didn't calculate it. We just said, D.5, sure, because that's a medium. And power, I don't know, 80% sounds good. Like, we literally just picked that out of the air. We didn't pick this. Alpha 0.05 is probably always stick with alpha 0.05. It's pretty rare we mess with that. It's changing. The world's getting a little bit better, but it's slow. Now, is the table? It's not going to show up on there. Okay, you can kind of see it. You can kind of see the table. So this is in the back of the textbook. So what you're going to look for, it's very hard to see this here, but you're going to see this is the 0.05 for alpha. Okay? And then here, this is, that's what we're going to read. So then we have to go read down through here. And we want to get to 0.8 right there. Do you see? I just went through, and there's 0.8. And then we're going to come across and read, and it says 2.8. And that's going to be put into a formula. So it's just a way to look at something. So let me show you the table here. So again, 0.05, that's our alpha. And we want a power of 0.8. So we look in here till we find 0.8, which is right here. Okay? And then we come across here and see what our delta is going to be. It's going to be 2.8. Like we just pull that out of a table. This is not hard to do, it's just weird, because we're saying, it's 0.5 and 0.8. And then the 0.05, like literally just look things up in a table. And now we just do some arithmetic. This isn't really even math. Well, it's a bit math. So, where the hell did I get n equals sigma divided by d squared? I've just rearranged the formula. Okay, so before we had, what did we have before? We had d equals, sorry, not d equals, get that wrong, Dave. Oh no, it's d equals delta, no, delta equals, right, d times the square root of n. Right, remember that? So then what we do is we say delta squared equals d squared times n, and then we do n equals delta squared over d. Yeah. Yeah, there you go. So that's how I did that. It's just cross multiplication. It's nothing magic. I didn't do any tricky math things, okay? So I took the values, literally one that we looked up, 2.8, and then d, which we literally, as I said, we just made this up. We said, yeah, 0.5 is good enough, so we use 0.5, and we divide those two numbers, 2.8 divided by 0.5, then we square it, we get 31.6. You need 32 subjects. That's literally it. Like, you need 32 people. If there is a difference of 0.5, and you want a power of 0.8, and an alpha of 0.05, you need 32 subjects. That's what that says. You'll find a difference, and you'll get that power. One thing that a lot of students get confused with, they mix up the idea that at 30 observations, a t basically becomes a z in a lot of respects. So people mix it up and say you always need 30. You don't. If you have a bigger difference, you need fewer than 30. All right. So, whoa, geez, it's so dark, so dim over there. I keep looking over there and there's nothing. So let's say we make the power 0.99. Ridiculous, but let's make it 0.99. So what I did is I went back to the table, and I just looked it up for 0.99, what the value for delta would be. It's now 420. So it's 4.2 now. Now when you do the calculations, which I'm going to do here, or which I did years ago, you need 71 people. So to go up, so basically go up by a factor of 25%, because 99, well, call it 100, is 25% more than 80, right? More than double the number of subjects. Is it worth getting that? No, it's not really worth getting that many, is it? It seems ridiculous. Right? Seems kind of ridiculous. Okay. The important thing about this is that this isn't that hard to do. And so few people do these things before they start research projects. I will tell you that the first thing, when I ask my students, when I'm having like my honor students, when we're our first meeting, and I say, outline what you want to do and what kind of design do you want to do. And I always ask them the same thing. I say, how many subjects are you thinking? How many participants? And everybody always says the same thing. Like, I don't know, 100? It's like, no, you need about 30. 100's not going to help you in any way. 30 should be fine, or 40, or sometimes I've looked and said, I don't know, 15 a group. What? Yeah. Oh, you'll find stuff. If you tested everybody in the world, you'd definitely find if it happened, but do you have that much time? No. And it's not worth it, right? So you can do these calculations. They aren't hard to do. Or you can even just literally look it up. There are tables online and decent, a little more advanced stats books than we have those tables literally in the back of the book. So I have power tables in a couple of my books, and I can easily look things up. You just read it for a graph. You might wonder, what the hell is delta? What is this? Well, it's got a name. It's called the non-centrality parameter. I'm only throwing this in because I know if I was being taught this, I'd say, well, nobody's told me what that is, and I'm going to tell you what it is. It's called the non-centrality parameter. We always assume HO, right? Whenever we do any statistics, we assume HO. We start out by saying, if HO is true, you know, remember we used to do that, right? That little decision rules, all that great stuff. Okay. So under HO, given HO, the expected value of T is 0. Now think about that for a second. I think I have a t-test formula. Yeah, right up here. If HO is true, then x bar equals mu. So yeah, you would expect it to be 0, right? Because you get x bar minus mu over whatever, no matter what it's over, it's 0. With the non-centrality parameter, what you're trying to find is how likely you're going to find a value of, again, sorry, you're going to think backwards. How likely is it that we'll find a value of delta that will allow us to reject the null hypothesis? So again, this is basically saying, do a t-test, but assume the difference is this big. We never do that. We always say assume the difference is 0. That's what, but it is just this. It's literally just a t-test formula. It just doesn't equal 0. The expected value does not equal 0. So if you ever want to know how the book's calculating them, it's just an old t-test formula. It's that simple. There's nothing magical going on at all. Really straightforward. The thinking's hard. Doing the things is easy. It's mechanical. It's just like do this, look at there, do that, do a very quick bit of arithmetic, and oh, it's 33 people, done. The logic of this stuff can be hard. Remember, the only way we can really determine the power of a test the only way we can really ever affect the power of a test practically is by having more observations. Because more observations allows us to decrease the overlap. So keep that in mind. Is the door, oh, I was going to say, I hope it's open. Okay, good. Because sometimes it'll pop. So there's that. The other thing is can you really know the power of a test? Like, think of the assumption you're making. The assumption you make to figure out the power of a test is you already know how big the difference is. And if you already know how big the difference is, you don't have to do the science. So no, you probably can't determine the power of a test. You can guess it. You can make a pretty good estimate, actually. but you really don't ever know it. This isn't something that's actually knowable. It just isn't. We can say this test is more powerful than that test. That's easy. But we don't know how powerful a given test is in a given situation. We can't know that. Because if we did know it, we would already know the difference between the alternative and the null hypotheses. And if we already knew that, why are we collecting data again? Right? Right. The upshot of this is just do this stuff. It takes you 10 seconds when you're figuring out how you're going to do your honors thesis. When you're sitting down thinking this through, it takes you 10 or 20 seconds literally to do this. Or talk to your supervisor as more advanced stats books and say, can you just look up the power we need, or the number of subjects we need for a power? It's really easy, and it'll probably save you some time. Because a lot of people, like I said, they're like, oh, I want to test 200 people. It's like, but why? You don't have that many hours in a day. You don't do that. You're insane. Questions? So what I want you to do for the upcoming test is to go through stuff and like ask yourself questions, that kind of thing. I think that'll really help put things into perspective. Arlo.
Like how does this work if you have like multiple groups, like a control group and a test group?
Okay, now let's say we have a control group, and let's say we have two control groups and an experimental group, right?
Yeah.
That's a pretty common thing. So now we have 3 groups. Now we're going to be obviously, you all know this, doing analysis of variance and then a t-test. Now let's think about how this thing all works. Remember when we figured out how to figure out what D is, we said how does n affect the statistic? And we look at the formula and it's the square root of n. Well, for analysis of variance, it's not the square root of n, it's n. Because it's squared. So you just put n in when you do the calculation. It's literally that simple. Like it's not a complicated thing. Yeah, good question. It's actually a really deep question. Well done. Did you think it was a deep question, or are you just happy that you got one?
I have multiple groups in my planned thesis project, so.
Yeah. Oh yeah. And you know what? Seriously, depending on who you work with, if it's like me or Paul, I know for sure, we have books sitting on our shelves that have power graphs. Like it's way easy. You don't even have to calculate. You just go, this number of subjects, this number of groups, I need to follow the line. Well, point 8, we'll follow this line. You need that many. So when I say do the calculations, what I'm trying to tell you really, not as much do the calculations necessarily, but find a way to figure out about don't just randomly pick numbers of subjects. Have some thought about it. And it doesn't take much. It just takes a couple of minutes of thinking, looking at what people used to do, have done in the past, but also just take a look at, like I said, if you have the ability to do the power calculation, or you have power graphs around, use those. So, all right. Okay. So,